It is the most recognized word in the world after OK. It is a beverage that has defined globalization, American culture, and the very concept of refreshment for over 130 years. Coca-Cola. Every single day, humanity consumes 1.9 billion servings of this dark, fizzy elixir. But have you ever stopped to consider the sheer industrial magnitude required to quench that thirst? Behind the red label lies a world of secret formulas, massive chemical engineering, and bottling lines that move faster than the human eye can track. Today, we step inside a mega factory, a facility spanning millions of square feet, operating 24 hours a day, 365 days a year, to witness the alchemy that turns plain water and sugar into liquid gold. The story begins not in the factory, but in a bank vault in Atlanta, Georgia. Inside a high-tech fortress lies a metal box containing a handwritten piece of paper. This is the formula for Merchandise 7X, the secret ingredient that gives Coke its distinctive taste. Only 2 people in the world are rumored to know the full recipe at any given time, and they are never allowed to fly on the same plane. While the romance of the secret formula is legendary, the reality of manufacturing is a feat of hard science. The first and most critical ingredient in Coca-Cola is not sugar or caffeine, it is water. A bottle of Coke is over 90% water, but you cannot just open a tap and fill a bottle. Municipal water tastes different in every city. It tastes like chlorine in Los Angeles, like minerals in London, or like iron in Mumbai. But a Coke must taste exactly the same in every corner of the globe. To achieve this consistency, the factory houses a massive water treatment plant. The water undergoes a rigorous purification process known as polishing. First, it passes through sand filters to remove large particles. Then, it enters the activated carbon towers. These giant silos are filled with charred carbon that absorbs chlorine, odors, and organic compounds. Next is reverse osmosis. High-pressure pumps force the water through microscopic membranes, stripping away salts, minerals, and impurities at the molecular level. What remains is neutral water, a chemically pure, tasteless canvas ready for flavor. This water is so pure, it would technically leach minerals from your body if you drank it alone. Now, the sweetness. In the United States, the sweetener of choice is high fructose corn syrup, HFCS, while in other parts of the world it is cane sugar or beet sugar. The sweetener arrives in tanker trucks or rail cars holding 50,000 pounds of thick, viscous syrup. This syrup is pumped into massive stainless steel silos. Inside the mixing room, the purified water meets the sweetener. Giant impellers stir the mixture into a simple syrup, but it is not Coke yet. This is where the secret base arrives. Drums of concentrated Coca-Cola concentrate, manufactured in only a few select high-security facilities around the world, are wheeled in. The contents of these drums are poured into the simple syrup. This concentrate contains the caramel color, which gives the drink its dark hue, phosphoric acid, which provides the tangy bite, caffeine, and the blend of natural vegetable extracts and oils, vanilla, cinnamon, citrus, and nutmeg, that make up the 7X formula. Once mixed, this becomes the final syrup. It smells intensely powerful. A single drop on your tongue would be overwhelming. It is waiting for dilution and carbonation. While the liquid is being prepared, the container is being born. Coca-Cola bottles are made of PET plastic, but they don't arrive at the factory as bottles. They arrive as preforms. A preform looks like a small, thick test tube with a screw top. It is the embryo of a bottle.
Transition temperature.
Using preforms saves massive amounts of space. A single truck can carry 1 million preforms, whereas it could only carry a few thousand full-sized bottles. These preforms are dumped into a hopper and climb a conveyor into the blow molder. This machine is a masterpiece of thermodynamics. The preforms travel through an oven tunnel, spinning on mandrels as they pass banks of infrared heating lamps. The plastic must be heated to exactly 110 degrees Celsius. If it is too cold, the plastic will shatter when stretched. If it is too hot, it will melt and droop. It must reach the glass transition temperature, a state where it is elastic and stretchable. The hot, soft preforms entered the blow wheel. A metal mold carved in the shape of the iconic contour bottle clamps around the preform. A stretch rod shoots down into the test tube, physically stretching it to the length of the bottle. Simultaneously, high-pressure air at 40 bar, 600 psi is blasted inside. Phoom! In less than 1/10 of a second, the tiny test tube expands, taking the shape of the mold. The mold opens, and a newborn bottle emerges. These machines can blow 80,000 bottles per hour. The bottles are air-cooled and sent flying down air conveyors held by the neck ring, racing towards the filler like a plastic army.
We have the syrup, and we have the bottles. Now we need the fizz. Carbonation is the defining characteristic of soda, but dissolving a gas, carbon dioxide, into a liquid is a battle against physics. Gas wants to escape. It wants to bubble out. To force the CO2 into the liquid, the factory uses a machine called the carbo-cooler. Physics dictates that liquids absorb gas better when they are cold. Think of warm soda going flat instantly versus cold soda keeping its fizz. The carbo-cooler chills the water and syrup mixture down to a near freezing 36 degrees Fahrenheit, 2 degrees Celsius. Inside a pressurized chamber, the final syrup is mixed with water at a precise ratio, usually 5 parts water to 1 part syrup. Then carbon dioxide is injected under high pressure. The cold liquid absorbs the gas, becoming saturated. It is now officially Coca-Cola, but it is unstable. If you poured it into a bottle now, it would foam over and explode like a volcano. This brings us to the filler bowl, the most complex machine in the plant. This rotary giant looks like a spaceship carousel. It holds the carbonated liquid under pressure. The empty bottles race into the machine, caught by star wheels that space them out perfectly. They are lifted up to meet the filling valves. Here, the engineering is brilliant. It uses a process called isobaric filling or counter-pressure filling. When the bottle seals against the valve, the machine doesn't pour the drink immediately. First, it injects CO2 gas into the empty bottle. This pressurizes the bottle to match the pressure inside the filler bowl. Because the pressure is equal, the soda flows down gently by gravity, without foaming. It clings to the sides of the bottle, filling it to the exact millimeter. If this pressure balance were off by even 1 psi, the factory floor would be covered in sticky foam in seconds. As the filled bottle lowers from the valve, it is technically open to the air. The headspace, the small gap of air at the top, is critical. A tiny jet of hot water or gas knocks the top of the liquid to create a small foam cap. This foam pushes any remaining oxygen out of the neck just milliseconds before the cap is applied. Oxygen is the enemy of flavor. The capper machine spins plastic caps onto the bottles at a rate of 20 per second. The torque is monitored electronically. Too tight and the consumer can't open it. Too loose and the gas escapes, resulting in a flat drink. Once capped, it is a sealed pressure vessel holding 60 psi of internal pressure. The bottles are warmed up slightly in a warmer tunnel to prevent condensation or sweating on the outside, which would make the labels peel off. Then they hit the labeler. A continuous sleeve of plastic labels is shot over the bottle and shrunk tight with steam, or a roll-fed paper label is glued at blinding speeds. Lasers etch the production gate and time onto the neck, a permanent record of the bottle's birth. Before they can leave, the bottles face the electronic inspectors. High-speed cameras photograph every bottle. They check the fill level. Is it too low? They check the cap. Is it crooked? They check the label. Is it straight? If a bottle fails any test, a pneumatic kicker blasts it off the line into a reject bin. The speed is so fast that the human eye sees only a blur of red and black. The perfect bottles march towards the packaging area. Robotic arms moving with the grace of a mechanical octopus grab groups of 6, 12, or 24 bottles. They are wrapped in plastic film, which is shrunk in a heat tunnel, creating the case. These cases are stacked onto wooden pallets by palletizer robots. These robots stack the cases in an interlocking pattern to ensure stability. A final machine wraps the entire pallet in stretch film, securing thousands of dollars of product. Forklifts, often autonomous guided vehicles with no drivers, pick up the pallets and rush them to the warehouse. This warehouse is a cathedral of commerce, stacked 50 feet high with beverages. From here, trucks will distribute them to supermarkets, vending machines, and restaurants within hours. The logistics are so tight that a bottle made this morning could be in your refrigerator by tonight. From the guarded vault in Atlanta to the high-speed filling valves in this mega factory, the production of Coca-Cola is a testament to the power of consistency. It is a process that turns a simple mixture of sugar, water, and gas into a global icon, replicated perfectly billions of times a day. It is the ultimate triumph of industrial engineering over thirst.